A phasor is a complex number we use to represent a voltage or a current waveform. So basically, using phasors allows us to get away from doing a lot of math with our sinusoidal equations. So we're going to talk about how to find the phasor from a voltage waveform, and it's actually fairly simple. The phasor voltage, for instance, is just the RMS voltage, and the angle is theta, or theta v, actually. So imagine that your sinusoidal waveform is really just a vector here on the coordinate system, and you're looking at your RMS voltage and your theta v for the direction, or for the location of that vector. And the current phasor is the RMS current and angle theta, where theta is the phase angle, or the phase shift of that sinusoidal waveform. Okay, let me pause here and just say that some text will use the peak voltage or the peak current in their phasor. Your Boylestad text that we use, Introductory Circuit Analysis, uses the RMS value, so that's what we're going to use as well. Okay, so for number 15, I'm going to express this sinusoidal equation in phasor form. So let's say that this is a voltage waveform. The RMS voltage would be 0.707 times the peak. In this case, 0.707 times 20 equals 14.14 volts. So the phasor voltage would just be the 14.14 at an angle of negative 180. So we just move the angle down. Now notice that this phasor includes information about the voltage itself, the peak. It's actually the RMS voltage, but we can find the peak from that. And it includes information about the phase shift. What it does not look at all is the frequency. Okay, so note that we can only use phasors for waveforms that have the same frequency, okay, because we're not accounting for that. So let's look at number 16, and we're actually going to work backwards for number 16. So this time we're given the phasor, but we need to find the current waveform. So to find our peak current, we would take our RMS current and divide by 0.707. So if we have 40 amperes divided by 0.707, we get 56.58 amperes. That's our peak current. Our theta I is 20 degrees. And we also need the omega to write our equation. We don't need it in the phasor, but we do need it for our equation, and that is just 2 pi f. And they gave us the 60 hertz in the problem statement itself because, again, we don't have it in the phasor. So 2 pi times 60 gives us about 377 radians per second. So that means our current waveform would be described by the peak current, 56.58 sine omega 377t plus 20 degrees. And there is our sinusoidal waveform that is described by the phasor. Alright, so why we want to do this is to make our calculations a little bit easier here. So let's imagine that we have a source current described by this equation and an I2 described by this equation, and we're looking for what I1 would be. Now we know Kirchhoff's current law tells us that I1 would be I sub s minus I2. So if we subtracted I2 from IS, we would get I1. Now, that's a little bit difficult to do with a sinusoidal waveform, so what we're going to do is use phasors, and we're going to write IS and I2 as phasors. So IS peak is 20 microamps, which means IS RMS is 0.707 times 20 microamps, or 14.14 microamps. And let's find the RMS value of I2. The peak value is 6 microamps. So the RMS is 0.707 times the 6 microamps, which would be 4.24 microamps. Microfarads. Microamps. Okay, so the phasor I sub S is 14.14 microamps at an angle of 60 degrees right there. And the phasor I2 is 4.24 microamps at negative 30 degrees. So if we're looking for I1, we need to subtract I2 from IS. Now, we don't add and subtract in polar form unless they have exactly the same angle or they're 180 degrees difference exactly. We can't subtract I sub S from I2 from I sub S in polar form unless we're using a calculator. Now, if you're using your calculator, you can subtract this just fine, just plug it right in. If you're not using a calculator, you will need to convert these to rectangular form first, and then you can do your subtraction. So when we do that, I plug this into a calculator and I get 14.76 microamps with an angle of 76.69 degrees. And we're asked to find the sinusoidal expression for I1, so we're going to convert this phasor back to a sinusoidal expression. So I1 peak is going to be that 14.76 microamps over 0.707, so 20.88 microamps. Theta I1 will be that 76.69 degrees. And so I1 as a function of time is 20.88 microamps sine omega, which we're not given omega, so we're going to leave it as a variable here as well, plus 76.69 degrees.